Welcome back. We're talking about conditional independence properties in directed graphical models and how you can derive them by just sort of looking at the graph. And in our little intuitive, or little at least exploring these sort of little special cases, the third case that we need to look at is the head-to-head case. And this is just when we have these nice little three random variables. So in the head-to-head case, we have A, B, and C once again. And now A and B meet C head-to-head. So what happens now? Well, let's try the same thing. Let's see what happens. So the joint distribution, this says the fact that A, B, and C respect this graph says that the joint distribution factors as the probability of A times the probability of B times the probability of C, given A and B. And now let's see if we can, what happens if we try to do the same thing. Let's just see what happens. So if we looked at the conditional probability, if we condition, let's go ahead and condition. Boom, we condition on C, then what happens? So we get a slightly different color. We get, there we go, that's better. We get the joint probability of A, B, and C divided by the probability of C. And now, what if we try to plug this in? Well, we don't get a probability of C to cancel. We could do Bayes' rule here, flip this around, but then we're still going to have a C. So things are not looking very good here. So let's put a question mark. Is this equal to probability of A? Before we had this, that it factored in this way, and that implied conditional independence. But does this apply here? It's not really clear. And the answer is no. Well, at least not in general. Not in general. This does not always hold in this case. So this is a little bit different. So let's see an example. So I worked out a little example of this. A little simple case to demonstrate this. So suppose A and B are we write Bernoulli for Bernoulli, random variables, and they're independent. And let's say that C equals 1. So these are like coin flips. So you could think about A and B as independent flips of a fair coin. And let's say that we're going to take C to be equal to 1 if they come out the same, if they're both heads, and 0 otherwise, else, if they're different. One's heads and one's tails. This is always a nice little counterexample to work with. Then, so if we're given A and we want to know whether A and B are conditionally independent given C. So say that we're given C, right? We're conditioning on C. We know C. We know whether they're equal or whether they're different. And now, suppose we learn A. Well, then we know B, right? Because if we know A is heads, and we know that C is 1, so we know that they're the same. We know A is heads, and we know they're the same. Then, of course, obviously, B is heads. So B is completely determined given A and C. And so therefore, this satisfies this little setup. It respects this graph because, right, these were independent. A and B were independent, and then C depended on A and B. So in this example, A and B are not conditionally independent given C. But what do we have? Do we have any sort of independence between A and B? Oh, well, I sort of said it already. I said that A and B were independent here, and it respected this graph. So let's see. Does that hold in general? That held in this case at least. Does it hold in general for anything, any distribution that respects this graph? Let's see. What happens if we let's try. Maybe I'll keep the same color. Let's keep it roughly the same color at least. So let's see, what does that mean? If A and B were independent, then we would need the probability of A and B to factorize the probability of A times the probability of B. So do we have that? Well, let's see. The probability of, let me try to get the right color here. Probability of A and B, is this equal to the product of the marginals? Well, this is the marginal over A and B, so that's equal to the joint summed over C. And what is the joint summed over C? If we sum over C, well, the sum moves through here. That's the probability of A times probability of C times the sum of the probability of C given A and B. And this is just 1, right? Because this is a conditional probability distribution over C. So this sums to 1, and we just get the product of the marginals, the probability of A times the probability of C, and that's a check. Yes. So what we have, we have in general, in this case, we do not have, in general, we do not have this, not in general. So let me say this. In general, but what we do have that A and B are marginally independent. So you could put, I mean, this would be sort of weird to say, but you could say that A and B are conditionally independent, given nothing. But that's kind of strange. So let's just say it this way. A and B are marginally independent. So those were some. So that's the third case. So the third case is that when they're head to head, then A and B are marginally, I mean, at least assuming there's nothing else here. I mean, this is just in the case. So far, we're just thinking about this simple little case with these 3 random variables. So it might be a little bit, maybe I shouldn't say in general. I mean, it could be that, it could happen, I didn't quite say that correctly. It could happen that they end up being conditionally independent given C. It could happen. I mean, it could, there could, some distribution, a distribution that satisfies this. You could come up with a distribution that respects this graph, for which they are conditionally independent given C. But not every, what I'm trying to say here is that not every distribution that respects this graph is conditionally independent given C. So that's what I mean by this. Okay, so what's the intuitive? So I will continue our little story here with the boiler. So what's the intuitive real world sort of situation here? So once again, the boiler is the protagonist. And we know that the boiler can set off the alarm through smoke or steam, sometimes on Christmas Day. And another reason why the alarm can go off, so a few days ago, they were testing the alarms. They were testing the fire alarm. And so when they're testing it, that can also set off the fire alarm. So let's think about, say I'm away from home and I don't know whether the alarm's going on or off. So I don't know the value of this random variable. I don't know whether the alarm is going on or off. Well, would I think that there's any relationship between the boiler coming on and then doing fire alarm testing? No, that would be ridiculous, right? I mean, what would the boiler coming on have anything to do with whether they're testing the fire alarms? So these events would be marginally independent. These would be marginally independent. If we don't know the value of the alarm, then these are independent. But what if we do know? Let's see. So what if we know? What if we condition on this? So as it turned out, before they started doing the testing, they gave us a little notice. Well, it was the night before, it was not long before, the night before, they delivered little envelopes to our doors, and those envelopes said, at 10 a.m. tomorrow morning, they are going to be testing the fire alarms. And so I knew that they were going to be testing around 10 a.m. in the morning. So when I heard the alarm at 10 a.m., I already knew that they were testing. So I knew that testing was going on. And so as a result, I didn't think that the alarm was being caused by the boiler. On the other hand, if I hadn't known that they were testing, say I didn't know, maybe I didn't. What if I didn't go, if I didn't go outside and didn't happen to get the little envelope, and I didn't know that they were testing, and I heard the alarm come on? Well, as it turns out, the only other 2 times that the alarm has come on was from those other 2 cases when there was smoke. It sent out the smoke, or there was the steam, and so I might think that bleeping boiler is at it again, that crazy thing. And so knowing the alarm, so my knowing that they were doing the testing, and knowing that the alarm came on, reduced my estimate of the probability that the boiler had come on, right? Because when I knew they were doing the testing, I attributed the fact that the alarm was going off to the testing. I said, oh well, of course, I know why that's happening. It's because they're doing the testing. But if I hadn't known that they were testing, I probably would have stormed down to the boiler room to see what the heck was going on. So the moral of the story is conditioning on this event, conditioning on the alarm, made these not independent. So they were not conditionally independent given this event. So maybe we should uncondition that for the general sort of case. So unconditioned. So the result holds. So for the head-to-head case, the result is that when you're not conditioned on C, then A and B are independent. Or in other words, they're marginally independent. Okay, so those were just a few little special cases of just a nice little 3-variable world in which we could play around and see what happens with these conditional independence properties. And next we're going to look at the d-separation property, which is a vast generalization of these very simple properties, and it's an extraordinarily useful tool for taking, you can take super complicated graphical models and just very, very quickly mentally trace through the graphical model and trace through different paths and figure out whether different random variables are conditionally independent given others. So that's going to be a very useful tool for us to get sort of under our belt. And maybe I should, so let me insert one caution here. These properties that we've been looking at here, we're focused on the case of directed graphical models, and there are also undirected graphical models, and the rules for undirected graphical models are different. So you need to just bear that in mind, that you have to use a different sort of set of rules to figure out conditional independence properties in directed graphical models than you use in undirected graphical models. Okay, so I'll see you back here soon, and we'll do d-separation.